All right, this is video 4, and we're going to cover 3 proofs related to the properties of the quadrilaterals. In total, there will be 18 properties, 18 unique properties between all of our quadrilaterals, and I'm going to help you prove 5 of them in total. This video will cover 3 proofs, and video 5 will cover 2 additional proofs. So it is very important that you guys write these down. If you didn't notice from class, I did not give you any notes to actually do this on. So I want you to do this on your own paper, and you'll include this in your total package of proofs, okay? So we're going to do proofs numbers 2, 5, and 6 in this video. And so in class, you will work together in some small groups and do the other proofs with each other and help each other out. Now, you might ask, man, we're going to have to do that many proofs? Are you going to give us any hints or anything? And yes, I will give you hints about how to set up and where to look at and how to prove each of those different proofs. But hopefully watching this video will start to give you an idea of the types of things you need to be looking for in order to accomplish these proofs. So let's start with this first one. It says, given we have a parallelogram, ABCD, we want to prove that the opposite sides are really congruent to each other. Okay, that was a property that you discovered in the computer lab, that opposite sides are congruent. So let's prove that that really is a true property in a parallelogram. Now, our given information is that we have a parallelogram. So the first line of our proof would be ABCD is a parallelogram. And now, what do we know is true about a parallelogram? Well, we know that the opposite sides are parallel, which they're already marked in my picture, but really I should have to state it. So I know that AB is parallel to CD, and I know, and I can just include this all in the same line, that BC is parallel to AD. And why do I know that's true? Well, I used the definition of a parallelogram. Okay. So I still need to show opposite sides are congruent. How am I going to do that? Notice I have already drawn in diagonal AC so that I have 2 triangles here. And you're going to be doing this a lot with your other proofs. You're going to have to show that triangles are congruent so that you can show that other certain things must also be congruent about those triangles. And those other things are the properties we want to prove here. So is there anything I could say is definitely true between these 2 triangles, knowing that I have 2 sets of parallel sides? Well, we could say this angle, BAC, and this angle, DCA, those are congruent alternate interior angles because I do have parallel lines. So I could go ahead and state angle BAC is congruent to angle DCA, and I just used, from a couple chapters ago, the alternate interior angles theorem. Now, I have another set of parallel sides, so I have additional alternate interior angles. I know that angle DAC and angle BCA are congruent for the same reason. So angle DAC is congruent to angle BCA. And I'm going to use my ditto marks here because I'm using the same reason. So again, the ditto marks just mean everything up above it basically is just rewritten, but you don't have to rewrite it. So at this point, I have angle in both triangles, which isn't a good shortcut. I need something sidewise. And if you notice, which I'm sure most of you have by now, we've got that reflexive side, AC. So AC is congruent to itself by the reflexive property. And so now I have angle side angle in both triangles. I know these triangles are congruent to each other. So triangle, let's call this one CAD, is now congruent to triangle ACB by angle side angle. Now, if these 2 triangles are congruent, that means everything else that I couldn't mark previously may now be marked congruent, such that corresponding parts of congruent triangles will now be congruent. So what else am I really interested in showing is true? Well, this, that the opposite sides are congruent. So let me shrink-a-dink this up just a hair so I can get just a little bit more space in here. And so now I can state, well, I now know that AD, two markings, and BC, they're congruent. AD is congruent to BC because of CPCTC. And I also know, with 3 marks here, that AB and CD are congruent for the same reason, more CPCTC. And what have I now shown? I've shown that the opposite sides are congruent. Now, do you have to write an additional line here that basically says opposite sides are congruent? You can if you want. I'm not going to be a huge stickler on it, but we could come down here and now say opposite sides congruent. What reason would we really give? Well, this one's kind of difficult. I guess you could say definition of congruent, or, this is why I'm not going to be a big stickler on it. But basically the reason is these two things right here. Those are the two sets of opposite sides. They're now congruent. So that's all for proof number 2. Now, proof number 5 is basically the converse of proof number 2. We're going to start out knowing we have opposite sides are congruent, and I want to prove this is a parallelogram. Okay? So before we really get started, let's think about what we would have to do to prove that something is a parallelogram. Well, number one, if something's a parallelogram, it must have 2 sets of parallel sides. So that's something we're going to have to show. We're going to have to show that the top and bottom and the left and the right, that they're really parallel. And how are we going to show that we have parallel lines? Well, we would have to show that, like alternate interior angles are congruent, or same side interior angles are supplementary. If you think back to the last proof we did, we used alternate interior angles. We already knew they were congruent because we already knew we had parallel lines. So what we would have to show is that the alternate interior angles are congruent, but not because of parallel lines. That's what we're going to have to get to. So sometimes in a proof, you can start out forwards, and you can kind of think about where you need to go and work backwards a little bit, and then somewhere in between is where you need to get to. And sometimes that is kind of a difficult task to accomplish. So where do we need to start here? We know ABCD has opposite sides that are congruent. So what's our given information? Is that AB and CD are congruent, and BC and AD are congruent. That was given to us. We were told that's true. Now again, we want to try to do some congruent triangles once again. And we don't really know any of the angles at this point because we don't know any parallel sides. But we do still know the reflexive side, that AC is congruent to itself. And that leads us to a shortcut. We now know those 2 triangles are congruent by side, side, side. So triangle ADC is congruent to triangle BC, or no, wrong way, CBA, right? ADC, CBA, yep, by side, side, side. Now, this is where we're going to make those angle connections. It would be fantastic if this angle and this angle were congruent, because they would be alternate interior angles. And alternate interior angles are congruent when we have parallel lines. And we could get our parallel lines from there. Now, can we say those angles are congruent? Well, let's see. This angle and this angle, notice they're right in between the 2 and 3 side markings, and this angle's in between the 2 and 3 side markings. So those 2 angles are corresponding parts of congruent triangles. Therefore, we may mark them as congruent. So we can say angle BAC is congruent to angle DCA by CPCTC. Now, since those angles are congruent, we can get that A and B is parallel to CD by using the converse of, and what type of angles did we just show had this special relationship up here? Alternate interior angles theorem. Now, we can't just stop there, because if we stop there, we've only shown that this thing is just a trapezoid and not a parallelogram. So we have to go a little bit further. But at least it's not going to be that much harder, because now we need to focus on these other angles, this angle and this angle. We know they're congruent as well. Oop, too far. There we go. I can put 2 angle markings on these 2 angles, because they are also congruent by CP/CTC. It's just another pair of CP/CTC information. And those are alternate interior angles. And so what may I conclude then is that AD and BC are parallel. And for what reason? Again, the converse of the alternate interior angles theorem. Now, I have successfully shown that I have two sets of parallel sides. So what does that mean this shape really must be besides just a regular old quadrilateral? We may now prove that ABCD is a parallelogram. And what reason are we going to give? Well, the definition of parallelogram. We showed that it had two sets of parallel sides, and so by definition, that is a parallelogram. And we're done. Okay, so this proof and the last proof are very similar to each other, except one kind of works forwards and the other one works backwards, which is why it's the converse of the other. The last proof we're going to look at is a tricky one, which is why we're going to do it together, definitely. And we're not going to do congruent triangles like you are most of the time when you do these proofs. So this one says, if we know that ABCD, if it has opposite angles that are congruent, then this thing really must be a parallelogram. It can't be a trapezoid, it can't be a kite. It's got to be some sort of parallelogram. Okay? So our given information is that we know angle A and C are congruent, and we know B and D are congruent. Now, you could draw in diagonals in here and try to find congruent triangles, but we don't really have to go that far. What we can do is focus on the fact of what all four of those angles together must create. And they must make 360 degrees because it's a quadrilateral. Now, what reason can we give for this? There's not really a set in stone reason we could use here. We could say it's the triangle angle sum theorem because technically a quadrilateral is made up of two triangles, and the reason why we knew triangles had 180 degrees was the triangle angle sum theorem. I'm just going to call it kind of the definition, or well, here, let's just do this. Let's call it a property of a quadrilateral. It's just one of the properties that it has 360 degrees in it. Now, you might ask, how is that really going to come in handy? Well, let's look. And here's where, again, we're going to kind of think more down at the bottom. If I know the last line of my proof needs to be ABCD is a parallelogram, and we're going to be using the definition of a parallelogram to prove that's true, if something's really a parallelogram, I need to show it has parallel sides. So if I need to show that B and C are parallel, then I need to have certain angles that are special. And so if we focused on this and this, we've got same side interior angles. And I would need to show that they are supplementary, that they add up to be 180. That's what we're going to try to focus on. So let's try to see if we can show that angles A and B are, let's see if we can show that angles A and B are supplementary. Okay, well, we've got A and B, but we also have C and D that equal 360. Is there anything that I could do to get rid of C and D? Could I substitute them out? Well, what else do we know C is equal to? Oh, well, C is equal to A, so let's make that substitution. And let's get rid of D. What else is D equal to? D is equal to B. So here I'm using the substitution property, not transitive, pure substitution. And so now if I look at this, I've got 2 angle A's plus 2 angle B's equal 360, and we call that a simplify step. We're just adding like terms over there on the left. And if I notice, all 3 of these terms have a 2 in common, a factor of 2. So if I were to divide everything by 2, that would leave me with that A plus B is equal to 180. And if A and B equal 180, that means they're supplementary. And if they're supplementary, that means I've got parallel sides. Sweet. So we can now say, let's see, A and B, they use B and C, right? So BC will now be parallel to AD, and I'm using the converse of, What type of angles did I just show had a special relationship? The same side interior angles theorem. Now, that's what I've got so far. This thing's a trapezoid. I need to go, again, one step further. I need to show this thing as a true parallelogram. Now you might think, man, are we going to have to start all the way back over and try to focus on like B and C or A and D so that we can get that A, B, and C, D are now parallel? No. We can use this line right here. If we knew A and B added up to be 180, let's focus on A and D. Well, I can just take this line that A and B equal 180, and instead of saying angle B, what else is angle B originally equal to? Angle D. So there I'm using substitution. And if A and D add up to be 180, that means these two sides must be parallel because A and D are same side interior angles. So AB is parallel to CD because, again, the converse of the same side interior angles theorem. So I have successfully shown, once again, that I have two sets of parallel sides. And because I have two sets of parallel sides, I've got a parallelogram. And there I'm done with that proof. So you will have two proofs like this where you have to prove that a shape is a parallelogram. So keep in mind what you had to do in order to prove that something's a parallelogram. Think about the steps before. So sometimes you can work a proof forwards a little bit, sometimes you can work a proof backwards a little bit, and try to find that magic point where they must come together. And so that's all for video 4. And you guys will start doing these other proofs in class in your small groups.